Welcome to the 14th lecture in our course on quantum mechanics. Every time I start one of these lectures, every time I think about the story I'm about to tell, I say to myself, this is the most amazing story yet. This is the simplest and most mysterious and most profound story I've told so far. Today, it might really be true. I want to tell you the story of a mathematical idea and what that mathematical idea means for the quantum world. What mathematical idea? A minus sign. Now, a minus sign seems like a pretty minor piece of mathematical paraphernalia. They don't even stick around. Two minus signs can annihilate each other and they go away. They become a plus sign. And it's hard to keep track of minus signs sometimes. It's hard to avoid making minus sign mistakes in a complicated algebra problem. Paul Dirac, the great physicist, used to joke that the trick was not to avoid minus sign errors altogether, but to make an even number of them so that they all canceled out. Well, I wish minus signs were so simple. It turns out, of course, that minus signs can be important. In quantum mechanics, a minus sign can make the difference between constructive and destructive quantum interference, and that's not a trivial matter. Okay, so let's begin. For the last several lectures, we've been talking about a very important minus sign, the difference between symmetric and antisymmetric states for identical quantum particles. For bosons, if you apply the swap operation that exchanges two particles to a quantum state, the swap acting on the quantum state, you get the state back. But for fermions, if you apply the swap operation to the state, you get the negative of the state back, -1 times the state. The difference is a minus sign. And what a huge difference that minus sign makes. As we saw, bosons are gregarious. They're more likely to be found in the same quantum state. Conversely, fermions are antisocial. They obey the Pauli exclusion principle. They can never be found in the same quantum state. Physicists put it this way. They say that bosons follow Bose-Einstein statistics, which means that boson properties, like bosons being in the same quantum state, can be especially important for things like light and for matter at extremely low temperatures and superfluids and superconductors and Bose-Einstein condensates. A physicist would say that fermions follow Fermi-Dirac statistics. Fermion properties determine atomic structure, chemical properties, nuclear structure, the solidity of matter, all kinds of things. So this minus sign, the only difference between bosons and fermions, this minus sign is arguably the most important minus sign in the world. But where does it come from? What is the essential difference between fermions and bosons? Nature provides a clue. It turns out there is a link between a particle's spin and the swap rule that it obeys. It turns out that bosons have spin 0, or spin 1, or spin 2. Their intrinsic angular momentum, their internal angular momentum, is always an integer. Fermions, it turns out, always have spin 1/2, or spin 3/2. And so on. So it turns out, for example, that electrons, protons, and neutrons are all fermions, and they're also all spin 1/2 particles. Now, Pauli himself was the first one to realize this in 1940, and physicists call it the spin statistics connection. Now, in order to figure out where the boson-fermion minus sign comes from, we're going to have to follow the spin statistics connection. We're going to have to go back and think about the properties of spin. Now, you may recall, back in lecture 10, there was another slightly funny minus sign that arose in lecture 10 when we discussed the spin 1/2 particles and their physics. And that minus sign had to do with rotating a spin state completely around by 360 degrees. What about that? That seemed funny because our intuition is that rotation by 360 degrees is like no rotation at all. I mean, suppose I turn around. I rotate myself by 360 degrees. My final relationship to the rest of the world, to the walls, the floor, the podium, appears to be restored exactly to my initial relationship. Facing the podium, I'm standing on the floor. And that's why we say 360-degree rotation, a turn by 360 degrees, is really the same as not turning at all. It's the same as 0 degrees. And you know, the same geometrical intuition holds for any geometrical shape. If you rotate a shape by 360 degrees about any axis, you'll wind up with something that seems to sit in the world in just exactly the same way. So the first point I want to make about this is that this is a kind of symmetry. Now, symmetry is a word that I've used a bit, so let me take a moment to give you a definition of symmetry. A symmetry is a transformation of something that returns it to exactly its initial condition. So for example, we talk about left-right reflection symmetry. An object is symmetric if it looks just the same after we reflect it, after we exchange left and right. So the capital letter R doesn't look the same when you reverse it. But the capital letter T does look the same. And that's why we say that the letter T is left-right symmetric, but the letter R is not. And this is why we called the state of a boson, of a system of bosons, symmetric. Because when we exchange two particles, that's a transformation, the quantum state stayed exactly the same. You swap, acting on the state, you apply swap to the state, you get the state back. Now, we can also have rotational symmetry. Any shape is symmetric under a 360-degree rotation. Any geometric shape is the same if we rotate it by 360 degrees. Some shapes do even better. The letter capital N, for example, is symmetric under a 180-degree rotation, a rotation by only half as much. And there's a useful exercise here. Write down the capital letters of the Roman alphabet and ask yourself, what are their symmetries? Can you reflect them? Can you rotate them? How does that change the shape of the letter? What things can you how can you transform the shape of the letter and get back the same letter? Now, some shapes are more symmetric than others. They have more symmetry. But every shape has that 360-degree symmetry. And that's why we think that 360 degrees is the rotation is the same as not rotating at all. The second point I want to make is that when we rotate, we're rotating one thing relative to everything else in the world. Rotation is about the relation between one thing and everything else in the world, the relation of its orientation to everything else. If there were an object that were the only thing in the world, the only thing in the whole universe, how would we know if it were rotating? How would we know if we'd turned it? There'd be no frame of reference to answer that question. So rotation is about the relationship between something and the rest of the world and how that relationship changes. And there is actually a surprise in the concept of rotation that I want to tell you about now. And to show you this, I'm going to borrow a magic trick, a useful magic trick from the American physicist Richard Feynman, based on an idea of Dirac's, to illustrate this surprising thing about rotation. So here is the apparatus for my magic trick. I have two pencils, and they're connected by a flexible ribbon. And for those of you who are playing at home, you can do this experiment yourselves. You can use, instead of a flexible ribbon, you can use your own belt, or you can make your own device that looks like this. We're just going to be turning things around, and we need something reasonably flexible that we can turn. Now, one pencil, let's suppose it's the pencil on your left. That pencil represents an object in the world, and the other pencil represents the rest of the world. And the ribbon connecting them is flexible, and can be moved around however we like. In fact, we're going to allow ourselves to even move it around the pencils if we wish, as long as we don't actually detach it from the pencils. The ribbon can go anywhere. All right, so here's the first part of our trick, experiment number 1 in our trick. We're going to start with the ribbon untwisted. And we're going to rotate this pencil by 360 degrees, 1 full turn. Okay, and we see that the ribbon between the pencils is now twisted. Or is it twisted? Maybe it just looks twisted. Maybe we can shift it around in space. Maybe if we shift it around in space this way, it will look less twisted. No, I just made it worse. Maybe if we shifted it the other way, it would get untwisted. And I try all kinds of things, and we find out that no matter how I move the ribbon around in space, it stays twisted. It stays twisted no matter how we shift it. So when we rotated this pencil by 360 degrees, we twisted its relationship with the rest of the world. The pencil looks the same, but the ribbon remembers. The ribbon remembers the rotation. So as far as the ribbon is concerned, something has changed. There's been a difference. Okay, that was the first part of the trick. And I don't think there are any surprises there. So now we're going to start the trick again. We're going to start with the ribbon untwisted. And we're going to rotate this pencil, but this time we're going to rotate it not by 360 degrees, but by 720 degrees. 2 full turns. Okay, so let's do it. We rotate it once, and again in the same direction. Voila. And we say, well, the ribbon looks pretty twisted. It looks twice as twisted. Or is it? Let's see if we can shift the ribbon around in space. Now, to be fair, I'm not going to rotate the pencil, although I might move the pencil a little bit in order to shift the ribbon around it. So let's suppose that I bring the ribbon around. Oh, that's not the right way. I bring the ribbon around this way. I'm just moving the ribbon around in space. I'm not turning the pencil. Okay. And I put it back. But now I find that the ribbon has no twist at all. The doubly twisted ribbon only appears to be twisted. The doubly twisted ribbon is not really twisted at all. The moral is, when we rotated the pencil by 720 degrees, we restored its rotation with the rest of the world. As far as the ribbon was concerned, it was as if no twist had occurred at all. The ribbon remembered a 360-degree rotation and was definitely twisted. But when you did the rotation twice, the ribbon was untwisted. This is an astounding conclusion. A 360-degree rotation is not quite equivalent to 0 rotation. But a 720-degree rotation twice around is equivalent to 0. So let me show you a second version of the demo that you can also do at home. You can use a coffee cup. I suggest that you use an empty coffee cup. Now I'm going to turn this coffee cup around. I'm going to turn it around in a consistent direction while holding on to it, and that's actually going to be quite difficult. I'm going to have to twist my arm around, but you'll see how it works out. So as I turn it around, it keeps turning in the same direction. I have to pull my arm way up here, and then at the end, I've turned the cup around once in a particular direction, and now my arm is kind of twisted around. But now let's continue the process. Let's keep twisting. Let's keep turning the cup in the same way. The cup is continuing to move in this, rotate in the same way. Now it's returned after 2 full turns, and my arm is untwisted. Try it at home. Okay, so what does all this ribbon twisting and coffee cup juggling have to do with quantum mechanics? Well, recall the spin of a spin 1/2 particle. Recall the quantum mechanical rules for that spin. In lecture 10, we described how a spin 1/2 particle could be rotated in space by using a magnetic field, and that acted on the spin like the magnetic field of the Earth acts on a compass, allows you to twist it around. Now, when we rotated a spin 1/2 particle by 360 degrees, and we went in 4 90-degree steps, we wound up with an unexpected minus sign. We began with the state up, and when we rotated that, we got the state right. And when we rotated that again, we got the state down. So far, so good. But when we rotated the state down, we wound up with the state minus spin to the left. And then when we rotated minus spin to the left, we came back to minus spin up. So when we rotated the spin by 360 degrees, we went from spin up to minus spin up, the original state with a -1 amplitude out front. Now it turns out that this fact is part of a general rule about 360-degree rotation. If you take a spin 0 particle, or a spin 1 particle, or a spin 2 particle, or so on, and you rotate by 360 degrees, the state just returns to the original state. The state goes to, if you rotate the state, you get the original state. But if you have a spin 1/2 particle or a spin 3/2 particle, then when you rotate the state, you wind up with the negative of the original state, just as we did when we rotated the spin up state by 360 degrees. Now, at the time, we decided that this didn't really worry us. We argued that this minus sign that shows up did not matter, because spin up and the negative of spin up, -1 times spin up, are physically equivalent states. Why? Because of the rule of probability, the Born rule. It says that the probability for any measurement result is just the amplitude, magnitude of the amplitude squared, but that's the same as the magnitude of the negative of the amplitude squared, and so you always get exactly the same physical results for any measurement with the state, the original state, and the negative of the original state, minus the original state. And so we said that extra minus sign didn't really mean anything physically. We just didn't have to worry about it. And I have to confess that I wasn't being strictly truthful. That's almost true, but it's not quite true. There actually is a clever experiment that can show the effects of this minus sign. So what I want to describe for you now is the thought experiment version of an experiment that can actually be done, that actually has been done in the laboratory. And the idea is to make a Mach-Zehnder interferometer. Here's our Mach-Zehnder interferometer. We promised whenever we were confused, we'd go back to the Mach-Zehnder interferometer. Here it is. We're going to make a Mach-Zehnder interferometer, but we're going to make it to work with neutrons instead of photons. And you can actually do this. The interferometer is actually a little bit smaller than this, but not much. It's actually made of a big single crystal of silicon, and all these parts are just carved out of the single crystal of silicon. Of course, we have neutron detectors instead of photon detectors, and we have to introduce a beam of neutrons from a nice, well-controlled nuclear reactor, and so we can make a neutron interferometer. And so let's talk about our simplified version. The neutrons enter in the upper beam. The beam splitters work just as before. So the state upper, that is, say, neutron in the upper state, becomes, at the first beam splitter, a superposition s, our favorite number, the square root of 1/2, s times upper plus s times lower. That's what the beam splitter does. We imagine that the sign change only happens at the bottom side of the beam splitter. And then when that state reaches the second beam splitter, exactly what happens with a photon happens for the neutrons, and you get constructive interference in one direction, destructive interference in the other, and the final state is upper. The neutrons always come out in the upper beam, never come out in the lower beam, because there's constructive interference in the upper beam, destructive interference in the lower beam. All the neutrons wind up in our green detector. Now, neutrons are spin 1/2 particles. So suppose we send them in with a spin up, just for simplicity, spin up. We can rotate that spin by using a magnetic field. So suppose we rotate the spin of the neutrons by 360 degrees. But now we're only going to do that for one of the beams. We're going to put our magnetic field on the lower beam. There's going to be a little region of magnetic fields. The neutron's going to fly through a little magnetic field. So we start out with the state upper. It goes to the state S upper plus S lower because of the first beam splitter. Now the lower beam passes through the little magnetic field, which produces a 360-degree rotation. And what do we get? We get S upper, the upper beam's unaffected, minus S lower. We produced a minus sign by the 360-degree rotation. So now our state is different. Instead of being S upper plus S lower, it's S upper minus S lower. And when it reaches the second beam splitter, the interference works in just the opposite way. The minus sign changes constructive interference to destructive interference and vice versa. And you have destructive interference in the upper direction, you have constructive interference in the lower direction. You never get the neutrons in the upper detector. You always get the neutrons in the lower detector. So you can see the effect of this minus sign. In fact, we can make a neat little chart, which is the amount of rotation versus the fraction of neutrons detected in the upper detector. And if we rotate the neutrons by 0 degrees, all the neutrons wind up in the upper detector. If we rotate them by 180 degrees, just 50% wind up in the upper detector, 50% in the lower. If we rotate them by 360 degrees, constructive and destructive interference trade places, and 0% of the neutrons wind up in the upper detector. If we rotate them by 540 degrees, that's 3 times 180, that's 1.5 times around, it's 50-50 again. And then finally, we only get 100% of the neutrons reaching the detector again when we rotate the neutrons by 720 degrees, 2 full turns around. Now, there's a quick little note I would like to make. When we rotate the spin by 180 degrees, that means that the neutrons in the upper beam are spin up, and the neutrons in the lower beam have now become spin down. And that means that the spin actually carries which path information. If you looked at the spin of the neutron, it would tell you which path it had followed. And because the spin then measures, in a certain sense, which path the neutron went on, the interference between the two paths completely disappears, and that's why you have a 50-50 probability distribution when you rotate the spin by 180 degrees. So that's kind of an interesting comment. But our main point is that to restore the original situation with the neutrons, we must rotate those neutrons by 720 degrees. That's an astounding fact, but it's a fact of experimental physics. You see, I seem to experience a 360-degree world. When I turn myself around once by 360 degrees, I see myself in the same relation to the world as I was before. And so I say, once around 360 degrees is just like not going around at all. But electrons and protons and neutrons see a 720-degree world. This is something that's very difficult to imagine. They experience something about the geometry of space that we do not quite see ourselves. Okay, we're almost there. Let's go back to Feynman's magic trick. Now we're going to take these two pencils to represent two identical fermions. The pencils, if you will, represent the spins of the fermion. And we're going to start with an untwisted ribbon. Now we're going to swap the two pencils. We're going to take the pencils and we're going to exchange their position in space without rotating them at all. But now, when we look at the ribbon, we note that the ribbon has become twisted. To untwist the ribbon, we're either going to have to swap them again or rotate one of the pencils by 360 degrees, and that will take care of the twist in the ribbon. Swapping the pencils twists the ribbon. Swapping the pencils actually involves an easy-to-miss relative rotation by 360 degrees. It's easy to miss it, but it's revealed by the twist in the ribbon that connects them. And that twist in the ribbon when we exchange the two fermions leads to the minus sign in the fermion exchange rule. What we have is the spin statistics connection, the connection between the intrinsic spin of a particle and whether it's a boson or a fermion. Particles which have spin 1/2 or spin 3/2 that pick up a minus sign when you rotate them by 360 degrees also pick up a minus sign when you exchange two of them. Now, we haven't quite explained the most important minus sign in the world. But what we have done is we have sort of reduced the mystery of it to its proper size. The universe is in some sense irreducibly mysterious, but there are some explanations we can give. We saw that spin 1/2 fermions had two weird minus signs. There's the minus sign from what happens when you swap two of them, the fermion swap rule. And there's the minus sign you get when you do a 360-degree rotation of the spin. And we've done several valuable things. First, using Feynman's ribbon trick, we showed that it was not at all unreasonable that a 360-degree rotation should be different from 0, but that a 720-degree rotation was the same as 0. That's not at all unreasonable. That's just exactly what the twist in the ribbon tells us. Second, we showed that this minus sign, though not directly observable, could actually affect an interference experiment with neutrons. So this is something that's real. Finally, we showed that the two minus signs, the minus sign in the swap operation and the minus sign in the rotate once around operation, were actually the same minus sign. That's the spin statistics connection. That's the secret behind the most important minus sign in the world. Okay, with that, we're going to conclude our discussion of the quantum physics of identical particles. The next thing we're going to want to do is to look more carefully at quantum systems composed of two pieces. And this will lead us to the idea of quantum entanglement between systems. And that will lead us straight back to the next act of the Bohr-Einstein debate. Einstein and his collaborators are going to argue that quantum entanglement shows that quantum mechanics cannot be a complete description of the physical world. That there are things about physics that are real, but not included in quantum mechanics. So the question we're going to ask is, are they right? And interestingly, what will Bohr say in response? And that's what we're going to do next time. I'll see you then.